Hey everybody. All right. So here we are. We're back at it again. Talking some more physics. We're talking about mechanical energy this morning. All right. So just before we start, just want to say I hope everybody's doing awesome. This is a very strange time. I won't physically see you for a while, but you guys can see me all here on the interwebs, in the ether. I'm just going to be talking to myself randomly in a room, and if I do sound weird, it's because it is a weird idea. It's a weird thing to be sitting here by myself, talking to myself about physics, and imagining you guys listening to me somewhere by yourselves, listening to me talk about physics. So, yeah, interesting times. All right, so hope you're all well. Hope you're all well, psychologically as well. So just take care of yourselves. Don't stress about this stuff. Just do your best. Stay safe. All right. Thinking about you guys. All right, moving on. Let's talk about mechanical energy. We need to talk about one of these fundamental physics ideas. Talking about work. Last thing we did was work. Remember, work is defined as. Remember, can you say it to me before I say it? Pause it right here and figure it again. And if you forgot, go back to your notes. Remember, it's force times displacement in the direction of the force. Displacement in the direction of the force. Right? If they're not in the same direction, we have to multiply by the cosine of the angle. We can have negative work, we can have zero work, you know, that sort of stuff. But what we need to talk about today is the work-energy theorem, which states that work that is done by some sort of process is the amount of energy that is transferred by the applied force. So the work that's done is the change in energy. W equals delta E. Okay? I'm just gonna need to. Where's my pen? Where did I put it? There it is. So work here. This idea of work is this. This is remember. This is work is equal to the change in energy to the system. Okay, how much work you do, that's how much energy we are adding or taking away from the system. So sometimes we can add energy, and sometimes we can take it away. If I'm lifting something off the ground, I am giving energy to it. I'm giving it potential energy, the ability to fall. If I let it go, I'm removing that potential energy, changing it into kinetic energy. So the work and if I lift it, I have to do work to lift it. If I let go, gravity's doing work and it's accelerating it. We got to think about who's doing what work on what and how. Okay? So let's talk about that right away. Gravitational potential energy. This is an easy one. Okay, we know that if an object is raised or lowered in a constant gravitational field, that means lab frame, that's here, right? We know that whatever we drop, no matter what we drop it against, right, everything will drop at the same amount, 9.81 meters a second squared, 9.81 newtons per kilogram. Right, that's this guy here, this G. Remember that G is equal to, I gotta back this up so it doesn't bounce, excuse me, 9.81 meters per second squared. Or another useful unit is 9.81 newtons per kilogram. Yeah, that's a useful thing to know, that another unit we can use for G is, hey, look, what did I do? Oh, I made a mistake. Down. If I put a vector sign, I gotta write down the direction. Okay? Towards the center of the Earth in the downward direction in our lab frame. Okay? So the magnitude of the force is going to be equal to the mass of the object multiplied by that G. And this time, if we want to talk about magnitude, we're only going to talk about the magnitude of our vector. Now, if I move something, if I change its position by h, let's say a height, this is only in the vertical direction. Okay, this h is only vertical, right? Because remember that the force we consider when we're doing work is only in the direction of the force, and we know that the force is up and down, so we only care about up and down motion. I'm doing no work against gravity by moving this back and forth, right? Because this is at right angles to G, or vertical, you know, in and out. Again, these are both at right angles to G, so it doesn't matter. The cosine, right? Cosine of 90 is 0, so it's gone. But if I move it up or down, I am changing its potential energy because I'm going with the force of gravity, because force of gravity is up and down, right? So work is equal to force times delta D here. And if I know that the force is just mg, I end up with this expression here that I'm going to give it another letter here. I'm going to give this a big letter U. Okay? So U we're going to use to define potential energy. And in this case, we're talking about gravitational potential energy. So the gravitational potential energy of an object, or its change in gravitational potential energy relative to a reference point. This is the tricky part here. So what's the height we're going to use? What's the height we're going to define? Right? What height do we use to express our potential energy? Is it from the ground? Is it from a desk? Is it from the ceiling? It doesn't matter, right? This idea is all based on a reference point. If I am using my desk, then my computer that's sitting on my desk has a potential energy of 0 relative to the desk. Relative to the ground, it's going to have a positive potential energy because it has the ability to fall to the ground. Okay, so that positive potential energy relative to the ground tells us that it can hit the ground. Relative to the ceiling, that would have a negative potential energy because I would have to lift it to the ceiling. I would have to pick it up and throw it at the ceiling. Don't do that. That computer would break and then I wouldn't be able to talk to you anymore. And that would be awful. Let's not do that. But for me to consider the reference point of being the ceiling, so if, let's say here, we're going to draw a wonderful Mr. Stone diagram. Here's the ground. Okay, there's the ground. Okay, and then there's this ceiling here as well. Okay, and then here's a desk. And here's an object on top of the desk. So relative to the desk, right, the potential energy will be 0 at this point relative to the desk because it's on the desk, right? The height relative to the desk is 0. So mg times 0 is 0. Right? It has no potential energy relative to the desk. Relative to the floor, right? If I'm going to use this as the floor, my potential energy will be positive, right? Because I had to lift it to get it to that point, right? For me to get it up to the ground, or if I drop it, it has the potential to fall. If I let it go, if I just move it off here, it's going to fall to the ground, and it's going to convert that potential energy into kinetic energy, and it's going to have speed, and it's going to hit the ground. When it hits the ground, then it's going to have 0 potential energy. Compared to the ceiling, if I have the ceiling as my reference point, right, then that would be negative because I have to lift it. I have to give it energy to get it up there. So all of these things are relative to the reference point, an arbitrary reference point that you have to decide. Okay, so that's the tricky point here. What is h measured compared to? Okay, keep that in mind. Let's do an example here. I'm going to lift a 10 kilogram mass to a height of 2 meters. How much work is done onto the mass? Well, that's pretty straightforward. So we know that work in this case is going to be equal to the change in potential energy, which is going to be equal to mg. In this case, I'm going to write delta h because it's my change in height. All right, so it's going to be, what's the mass? 10 kilograms multiplied by 9.81 newtons per kilogram. Notice I use the units newtons per kilogram because now I can just cancel out kilograms, and I'm left with newtons. And I'm going to multiply by, how many? It was 2 meters. All right, so what's that work out to? 10 times 2 times 10, not using sig digs, 2 times 10 times 9.81, and that's going to be 200. That's going to be 2 times 10 to the 2. What are the units? It's potential energy. Energy is measured in joules. All right. So the work that I have to do is I have to do 200 joules of energy of work. Sorry, 200 joules of work onto my mass, my 10 kilogram mass, to lift it up 2 meters. Okay, so I'm giving it potential energy. I had to do the work. This is a positive a number because I am giving that mass energy relative to, in this case, the ground. The reference point here, because this is height measured from the ground. So the reference point is, in this case, the ground. All right. If I use the 2 meter point as my reference point, then I would have 0 energy at the end, and I would have negative 200 at the beginning. That's a little bit tricky. We'll have to keep that in mind there. Okay. All right, what about kinetic energy? How do we define, in a quantitative sense, kinetic energy? All right, let's figure this out. So, what are we going to have here? We have object at rest. Okay, at rest. This is pretty important. It's currently at rest. We're going to use a force F to accelerate it over displacement delta d. It undergoes an acceleration a, and it reaches some new speed vf. Can I change this? I'm going to change this here. Let's get rid of that. v2 for our nomenclature, okay? Make our life a little bit easier. All right, so what do we know? We have displacement, velocities, acceleration, no time. So remember, what equation can we use for that one? So let's write that. Remember that equation, v2 squared is equal to v1 squared plus 2a delta d. That's the expression that we can use to determine any of those things. Right? We have no time. If we had a time here, we might use one of those time expressions, but we don't. So let's just use that. All right. So rearranging this for acceleration, right? I could get the acceleration is the difference of the squares of the velocities divided by 2 delta d. Okay, so that expression now tells me my acceleration. I'm going to need that expression in a second because I know that work is equal to my change in, I'm going to use a big K to represent kinetic energy here. So K represents kinetic energy, U represents potential energy. And I'm talking about the change in kinetic energy. This is my WorkEnergy Theorem, remember? This is my WorkEnergy Theorem. Tells me I can do that. So that's going to be equal to, again, this is going to be force times displacement. Newton's second law tells me that force is equal to, Newton's second law, F equals ma delta d again. All right. And who cares about the mass? We're going to leave that there. But I have an expression here for acceleration. So acceleration is going to be v2 squared minus v1 squared all over 2 delta d. And then my whole expression is multiplied by delta d. What do you see there? What are we going to do? Delta d divided by delta d. Goodbye. You are the weakest link. Goodbye. So I'm going to rewrite this a little bit differently. Instead of saying divided by 2, I'm going to say multiply by a half, because dividing by 2 and multiplying by half are the exact same thing. So 1/2 m, and again I have v2 squared minus v1 squared, which is going to be my expression for my change in kinetic energy. This is my change in kinetic energy. Now, what's my reference point going to be here? Previously, when we were talking about heights, I used some height as a reference point. Now we're talking about velocities. And in this case, we said, remember that at the very beginning, I said that the thing has to be at rest? So that means that my initial velocity is going to be 0. Okay? So my reference point is from rest. So anytime I talk about an object having, hey, you can't see that. Whoopsies. Okay. Right, when I was talking about a reference point, now a reference point is going to be the rest case. I'm going to accelerate it to a new velocity, v2. Okay, from v1 equals 0 to a v2. This is the energy required to get something to that velocity, something that has a mass m and a velocity. So this is, I'm going to now call this just k. This is my expression here for kinetic energy of an object. I'm going to define kinetic energy to be from rest. Now this leads us to this wonderful Newtonian idea of, every frame of reference is correct. So it doesn't matter what frame of reference I'm in, I can always define a kinetic energy in that frame of reference. But it can be different, right? In the moving frame, if you're in the car, let's say, you're inside the moving frame, you're inside the car, an object that you're holding has no kinetic energy with respect to the car, right? But if you go outside of it, and if you're observing the object being held inside the moving car, it'll have kinetic energy with respect to you, the rest observer. Okay, so the reference point now is, are you moving or are you not moving? Okay, but we can use this expression here, half mv squared. This is one of those ones that are on our formula sheet, one of these incredibly famous, probably should be memorized formulas, that the kinetic energy is half mv squared. Okay, which is actually an interesting point in terms of energy. You think of, okay, think of a car traveling at 50 kilometers an hour compared to a car traveling at 100 kilometers an hour. How much more energy does the car traveling double the speed have? Is it double the energy? If I double an object's speed, do I double its kinetic energy? No, because I have to square that. So this will be instead be quadruple. If I double an object's speed, you quadruple its energy. All right? So to go from 50 kilometers to 100 kilometers an hour, that doesn't double its energy, it quadruples it, because we are squaring the velocities. Right? So that's kinetic energy. So let's go back here. We have our potential energy formula here. Oh, gravitational potential energy and kinetic energy. These are the two energies that we're going to be typically using to define mechanical energy. How much is it moving? And what ability does it have to fall? So let's do a quick example here with kinetic energy. Determine the energy of a baseball traveling 169.1 kilometers per hour. That's a random number. Okay, so let's see. How do we convert that to? So let's do this quickly. This is A. So 1 point. So velocity in this case is going to be 169.1 kilometers per hour, which is the same as. That's 46.97 meters a second, right? Because we can't use kilometers per hour. They're silly units. Oh, look right there. What's that? What is he there? Where is he? Where is he? Oh, there's a foot. There's a Charmander foot that my son left in here. Interesting. All right. Oh. So, how are we going to calculate this energy? So, K, in this case, we're only caring about its kinetic energy. It's going to be 1/2 times the mass of a baseball. What's the mass of the baseball? Let's Google that quickly. Mass of the baseball. Okay, so mass of a baseball is 145 grams. Okay, so this is going to be 0.145 kilograms multiplied by 46.97 meters a second, and that works out to squared times 0.14 divided by 2. So that is 160. What are the units on that? It's energy, kinetic energy, so that's joules. Okay, so 160 joules. Let me just check that again. Make sure I got that right. Yep. Okay. 160 joules. Right? So that's my kinetic energy of a, hey, I did something I shouldn't have done there. I should have put the formula here. So just make sure you put the formula first. mv squared. Okay. All right. I'm running out of room here to do this, but let's do the next one. So an electron, it travels, what the heck does this mean? That's not a speed. 0.1 c. What the heck is c? C is the speed of light. Okay, it's 3 times 10 to the 8 meters a second. So sometimes you can express things as what percentage of the speed of light. So this would be 10% of the speed of light. So an electron travels at 10% of the speed of light. It's in a cathode ray TV. So one of these monitors like this, there's a little heat source in the back here. It produces electrons. And then they're accelerated with an electric field. They hit this phosphorescent screen and they create a picture. So again, kinetic. Sorry about that. So kinetic energy is again 1/2 mv squared. So we're going to get 1/2 mass of an electron is 9.1 times 10 to the negative 31 kilograms. Ridiculously small. So it'd be 30 zeros and then 91. Then the speed. So this is going to be 3 times 10 to the 7 meters per second, all squared. And you're wondering where I got that 7 from. So the speed of light, c, is equal to 3 times 10 to the 8 meters a second. And if I know it's 0.1 of that, so I'm going to change this to a 7. So I just move the decimal 1 to the left. It becomes 3 times 10 to the 7 meters a second. All right, so if I square that, so 3 to the power of 7 squared times 9.1 to the negative 31 divided by 2. Oh my, that's very little energy. So that's 4, what's that going to be? That's going to be 4.1, let's say. 4.1 times 10 to the negative 16 joules. Okay? Very, very small. Excuse me, very, very small energy. And it hits that little phosphorescent screen and it creates a picture. Right? So half mv squared is our formula we're going to use here. Plug in, just don't forget the squares. They're easy to forget. Okay, write the formula out. Just quickly, is the units going to work out? Are we going to get the correct units here? So what are we getting? We're getting kilograms multiplied by meters per second, and then I square that. So what's that going to work out? That's kilograms meters squared per second squared, which is joules. Okay? So, those are the big ideas for today. Half mv squared is kinetic energy, and oh, just quickly before we start, remember these numbers, what that number represents is the energy required to bring that baseball from rest up to that speed, or bringing that electron from rest up to that speed. These are all relative to a reference point, and in this case, it's the rest frame. So if we go back to the height one, right, this is all relative to reference height, mgh, where h is measured from some reference height, and then half mv squared is measured from a reference velocity. Okay? All right. So what I want you to do now, guys, is go to the website. There's problems there. Here, these are the problems. They're called mechanical energy problems. They're on our website. I will shortly be posting the answers to them. It does give you most of the answers here, but I'll work them out and I'll post them to our Weebly. And I hope you're all well. Hope everything's okay. We're hanging in there here. I got 4 kids that are running around like crazy. Thank goodness they don't come barging in here when I'm doing this. Sometimes they do, and I have to stop and pause it and go from there. But maybe they'll have a little cameo at some point. But I hope you guys are doing well. Take care. Stay safe, and I'll see you later.